Hi, thank you so much for watching this video presentation, and many thanks to the organizers of this 2022 Cosmology from Home conference for all their work and support putting this together. My name is Emmanuel Schaan, and I'm a Chamberlain Fellow at the Lawrence Berkeley National Lab. And I would like to talk to you about cosmic microwave background secondary anisotropies. So I'll explain what that is in a moment. And really what this talk is about is combining data from the cosmic microwave background, this first light from the Big Bang, with data from the large-scale structure of the universe, which is the large-scale distribution and clumping of galaxies and matter, and specifically how to use this cosmic microwave background as a backlight for the large-scale structure in order to illuminate some of its invisible properties, much like you would look at the watermark on a banknote by placing it in front of a light. So in order to explain what those CMB secondary anisotropies are and to motivate why they're interesting, I thought I would start by telling you the scientific questions that I'm trying to answer with them. And to do this, it helps to take a look at this timeline of the history of the universe. So all the way on the left, what you see is the Big Bang 14 billion years ago, and time passes towards the right all the way to today, 14 billion years after the Big Bang. Now, there's a lot that we know about the composition, the history, the evolution of the universe from many, many different probes and observables. But for the purpose of this talk and for the purpose of CMB secondary anisotropies, I'll be focusing on two main classes of observables, which are first, the cosmic microwave background, the CMB, this first light that was emitted 400,000 years after the Big Bang. And sorry, this CMB tells us about the initial conditions of the universe. When you look at the CMB, what you see is the baby picture of the universe. And so all these blue and red spots, these cold and hot spots, tell us about overdense and underdense regions in the early universe. The second class of cosmological observables that I want to talk about today is the large-scale structure of the universe. So again, how galaxies and matter in the universe are clumped together. And so on this figure on the right, every green or red dot that you see is a galaxy. And as you can tell, they're not uniformly distributed. They are clumped. They are clustered. And so most of the game of cosmology has been to try to match the initial conditions of the universe from the CMB to the final conditions of the universe from large-scale structure surveys. And if you're able to match these two statistical properties of the initial and final conditions, you may have a good model for the evolution of the universe. And so you may have a good model for the 14 billion years of evolution under gravity. And at the moment, we have such a good model, the standard model of cosmology. It has been extremely successful at reproducing a large number of observables. However, it relies on a number of components that are not part of the standard model of particle physics. And so these components are dark energy, the dominant energy component in the universe that's responsible for the accelerated expansion of the universe. This mysterious dark matter, 5 times more abundant than the ordinary matter. And this hypothetical phase in the early universe, inflation, possibly responsible for generating the initial conditions of the universe. And so here the motivation for using those cosmic microwave background and large-scale structure data sets is really to answer some of these fundamental physics questions, to use the universe as a fundamental physics lab, and learn quantities like the energy density of dark energy, its evolution with time, or in other words, the equation of state, properties of the dark matter like its potential interactions or its thermodynamics, and the properties of this hypothetical inflationary phase of the early universe. I also wanted to point out another fundamental physics question that we are bound to help answer using cosmic microwave background and large-scale structure data, and that's the question of the neutrino masses. So neutrinos are some of the most abundant particles in the universe, almost as abundant as photons, and yet there's very much we don't know about neutrinos. In particular, while we know that they do have a mass from neutrino oscillation experiments, we do not have an accurate measurement of the value of this mass. And this is a place where cosmology can help. This is a place where we can use the universe as a lab to probe gravity. And for probing gravity, the universe is a unique particle physics lab. The way it works is as follows. We know that neutrinos are at least 0.5% of the matter density today. And so naively, you may think that in order to learn about their masses, you will need to measure the large-scale structure of the universe to about 0.5% precision. However, you are helped by the fact that the gravity from these light neutrinos has been at work for about 14 billion years, and their gravity has suppressed the clustering of the rest of the large-scale structure, causing an 8-fold increase in the effect, meaning that the effect of neutrinos on the large-scale structure is actually a 4% effect, and 4% is well within the precision of upcoming large-scale structure experiments. So visually, this is what it looks like. On the left and right, you see cosmological simulations with massless and massive neutrinos. And by eye, they look almost identical, except that on the right, you might see a bit more blue, meaning that the small-scale structures have been erased by the gravitational pull of neutrinos. And in fact, combining CMB and large-scale structure data in the next decade, we expect to measure those neutrino masses to about 20 millielectron volts. And to tell you what that means, this is a third of the minimum possible value of their masses. And so we expect at least a 3 sigma measurement of neutrino masses. So again, scientific questions, the motivation for the CMB secondaries, learning about dark energy, dark matter, inflation, and the neutrino masses. So how do we do this? And this is where I'll explain what those CMB secondary anisotropies are. So I told you at the start that the cosmic microwave background tells us about the initial conditions of the universe, about the baby picture of the universe. And this is mostly true. It is true for all of the CMB photons that have traveled for 14 billion years throughout the universe unimpeded and that have reached us. However, this is not the fate of all CMB photons. In fact, along their way between the CMB and us, the CMB photons' trajectories get deflected. They get pulled by the gravitational pull of galaxies and halos in their large-scale structure. And as a result, the properties of the large-scale structure, their gravitational potential, or in other words, their mass, gets imprinted on the cosmic microwave background. This is an effect called gravitational lensing. And loosely speaking, I'll describe them as mass shadows, meaning any imprint from a mass in the large-scale structure onto the CMB. Another key type of imprints of the large-scale structure on the CMB has to do with scattering. So as CMB photons travel towards us, about 5 to 6% of them will hit a free electron in plasma or hot gas around galaxies, and this will deflect their trajectories. What this does is it imprints yet another property of the large-scale structure, no longer the mass, but the gas density or the gas thermodynamics onto the CMB. And so those Thomson scattering effects imprint another type of shadows into the CMB, shadows of the gas. And what's particularly interesting about these anisotropies of the CMB, so these are called CMB secondary anisotropies because unlike the primary anisotropies that come from the early universe, these were imprinted later when the CMB photons travel through the large-scale structure. And what's particularly useful about those CMB secondary anisotropies is that they reveal properties of the large-scale structure that you would not be otherwise able to see by just simply doing a galaxy survey. So mass is not a direct observable, and lensing reveals it. So CMB lensing, just like galaxy lensing. And scattering tells you about the gas, which, as I'll talk about in a moment, is really hard to see in any other way. For completeness, I thought I would mention the other CMB secondary anisotropies. So I talked about lensing and scattering. There's actually a variety of imprints of the large-scale structure onto the cosmic microwave background. And you may have heard all of these names listed here on the left. And I thought this slide could be helpful to put them in perspective, to organize them, and to show you how they all come from products of a few key dimensionless parameters. And so once you understand those key dimensionless parameters, you can generate all of the CMB secondary anisotropies. So these parameters are the lensing deflection, which is typically arc-minute in size. It tells you about the mass of halos. How much the gravitational potential from the large-scale structure evolves as the CMB photons are traveling through them, another small number. The Thomson scattering optical depth, or how opaque the gas and the electrons around halos are to CMB photons. And then properties of the gas, such as the temperature of the electrons compared to their rest mass energy. So this tells you about the thermal velocity, and bulk velocity, so the bulk motion of the gas around those halos. And finally, these numbers you can compare and also combine with the typical size of the primary CMB anisotropies, those early universe fluctuations that you see in the CMB. And so when you take products of all of those dimensionless number, you generate basically two classes of CMB secondary anisotropies. The first class has to do with potential effects, so effect of the gravitational potential, and these include lensing, the integrated Sachs-Wolf and the Riesz-Jama effects, and things like the moving lens effect, also called the Birkinshaw and Gull effects. Other CMB secondary anisotropies that involve Thomson scattering. There's many of them: screening, kinematic, and thermal Sunyaev-Zel'dovich effect, which I'll tell you a lot more about in a moment. Polarized scattering, and finally, you can take products of all of these effects as soon as you include multiple scattering or multiple lensing events. But again, for the purpose of this talk, I'll focus mostly on lensing, so shadows of the mass, and scattering, those thermal and kinematic Sunyaev-Zel'dovich effects. In case this was a bit dry, just to show you visually what it actually looks like, here on the left is a map from the Planck satellite at 150 gigahertz, and on the right is a map at the same frequency from the Atacama Cosmology Telescope a few years ago. And what you can see is that when you crank up the resolution to about 1 and some arc minutes, what you find is those point sources that start to appear. And so unlike the degree scale blobs that are the primary fluctuations, these point source-like objects are the secondary anisotropies that tell us about the large scale structure. And so if you stare at this image on the right, you'll see a bunch of red dots. This is emission in far infrared from active galactic nuclei or dusty star-forming galaxies. And you might be able to see blue dots, temperature decrements, and these are the Sunyaev-Zel'dovich effect, shadows of the gas, that I'll tell you a lot more in a moment. In fact, to just drive this point home that CMB experiments are starting to have a high enough resolution to not just resolve degree scale blob, but actual astrophysical objects. Here are a number of targets that you may be able to observe from your backyard with an amateur telescopes. And on the left, you see their image as seen by Acton Planck. So we start to really do sort of classic astronomy with the CMB. So these were the CMB secondary anisotropies. I would just like now to give you a sense for why now is a good time to study these effects. And the reason for this has to do with a number of experiments that are coming online in the next few years. So here's a timeline with many, many exciting experiments that are going to push the boundary in terms of resolution and sensitivity for CMB experiments compared to what we have currently. And I thought I would just highlight the ones that I have been a part of. So this advanced Atacama Cosmology Telescope, whose data I'll tell you a bit about in a moment. Simon's Observatory, one of its successor, which will really push the sensitivity a lot, and for which I have been co-pipeline lead for the CMB lensing and KSZ working groups. And finally, CMB-S4 or CMB stage 4, which will further push the sensitivity. So a lot of exciting data sets coming soon, and these data sets perfectly suited for CMB secondary anisotropies because of their high resolution, high sensitivity. And as I'll show in a moment, detecting those CMB secondary anisotropies requires combining data from the CMB and the large scale structure. And on this front, we also have many exciting experiments coming online. So I just wanted to highlight DAISY, the Dark Energy Spectroscopic Instrument, which basically completed its first year of observation. And so here we're talking about 3D positions for tens of millions of galaxies, more than we've had with any previous experiment. The Vera Rubin Observatory, which will observe the position of not tens of millions, but billions of galaxies, although in 2D as opposed to 3D. And finally, the SphereX satellite that has been approved, and that will have a lot of exciting science coming with it. So this is all I wanted to say about introduction for CMB secondary anisotropies, the key science questions we want to answer with them, so dark energy, dark matter, inflation, neutrino masses, what they are, potential and scattering effects, and why now is a good time to look at them. So in the rest of the talk, I thought I would talk about two of these CMB secondary anisotropies, so lensing or shadows of the mass, and then scattering or shadows of the gas, and finally a few future directions. So if you have any question up to this point, please feel free to ask them asynchronously on Slack right now, or write them down so you can ask them during the live Q&A session. So let's move on to the first part of this talk, talking about mass shadows or gravitational lensing of the cosmic microwave background. And in this part of the talk, I would like to show you how understanding a deep analogy between how the lensing of the cosmic microwave background and the lensing of galaxies works allows us to improve our measurements of both CMB and galaxy lensing. So to get started, here's a brief overview for what cosmic microwave background lensing looks like. So again, as the CMB photons travel from early universe to today, from left to right on this schematic, they do not travel in a straight line, this blue dashed line, or rather they travel in a straight line in curved space-time. So their paths are distorted by the gravitational pull from the large-scale structure. And this results in deflection of those CMB photons that are typically arc minutes in size, but coherent on degree scales. And this coherent length has to do with the coherent length of the large-scale structure. Lensing conserves surface brightness. What this means really is that it's simply a remapping of the CMB image. So the CMB that you see here at X is what the unlensed CMB T0 would have been at position X minus D, where the difference between the position here and there is this deflection field D. And in the simplest approximation, this deflection D really tells you directly about the gravitational potential phi of the large-scale structure. And we typically parameterize by this convenient quantity kappa, the lensing convergence. So the goal of CMB lensing is to estimate this map of the lensing potential phi or the lensing convergence kappa. And this is what a typical convergence kappa map looks like. And to show you the effect on the CMB, the effect of lensing, here's a simulation. So what you have here is an unlensed CMB map. And if you lens it with the kappa map that I just showed you, what you get is this map. So if I flip between the two, what you might see is very small deflections, arc minute in size, but deflections that are coherent over large scales, again, coherent over degree scales. And so ideally, you would look at the unlensed map, you would look at the lensed map, and you would look at the difference between these two. This would tell you about the lensing deflection. However, of course, in real life, you only get to see the lensed CMB. And so the way we reconstruct the lensing convergence is as follows. We use the fact that lensing breaks the statistical isotropy of the cosmic microwave background. Operationally, what it means is that the small and large scale Fourier modes in the CMB, which would normally be uncorrelated, become coupled. And so naturally, the way we measure lensing is by estimating this coupling between small and large scales. And to estimate this coupling, we measure the covariance between small and large scales. So our estimator is quadratic, a quadratic estimator, product of small and large scales. So this is how CMB lensing works and how we estimate it. I just wanted to emphasize why CMB lensing is so important. And so what you see here on the right, this table shows you the key science goals of an experiment like Simon's Observatory. And things will be very similar for CMB-S4. And I don't mean for you to take in all of these numbers, but I just wanted to circle in red the science goals for which CMB lensing is crucial. And as you can see, it's basically all of them. And so these are the scientific questions that I highlighted at the start. And for pretty much all of them, you do need to measure that CMB lensing. The good news is with an experiment like Simon's Observatory or CMB-S4, we expect very small statistical error bars. So detecting CMB lensing at a significance of 100 for SO or 400 for CMB-S4, and so really sub% precision on CMB lensing. So this all sounds great. Let's do CMB lensing. However, there's a key hurdle in our ability to measure CMB lensing, and that hurdle is that of extragalactic foregrounds. And what this means really is that when we look at the CMB, what we see is not just the lensed CMB, but a number of other effects added on top of it. Some are those CMB secondary anisotropies that I just talked about, those thermal and kinematic Sunyaev-Zel'dovich effects. They can also be infrared point sources or radio point sources. And if you don't do anything to remove these extragalactic foregrounds, they can significantly bias your lensing. So what you can see on this plot is the fractional bias to the CMB lensing convergence power spectrum as a function of Fourier scale. So small scales are on the right, large scales on the left. The gray band shows you the expected statistical uncertainty for SO. And so you would like the bias to be close to 0 and definitely within that statistical uncertainty. And instead, what you find with this standard quadratic estimator is that the bias is extremely large, much larger than your statistical error bar. And so if you don't do anything about it, this is what you get. And if this is what you get, you might as well throw out your CMB lensing measurement. So this is a key challenge that really needs to be addressed to be able to answer all of the science questions that I showed you a minute ago. And one key way to address this challenge is as follows. And it has to do with an analogy between lensing of the CMB and lensing of the galaxies. And so I told you that lensing of the CMB is measured with this quadratic estimator. In galaxy surveys, it is usually measured by looking at shear and or magnification. And there the effect is that galaxies on average are supposed to be round. And so if you're in a patch of the sky that is magnified, the size of the galaxy or its brightness increases. And if you're in a patch of the sky that is sheared, the image of the galaxy gets squeezed into an ellipse. Well, it turns out if you look under the hood of the CMB lensing quadratic estimator, you find a quantity that's analogous to the round shape of galaxies. And the analogous quantity is the round hot and cold spots of the CMB, or equivalently in Fourier space, these hot and cold spots look like those acoustic rings, which are on average round. And so if the patch is magnified in Fourier space, those rings get compressed. And if the patch is sheared in Fourier space, those rings also get squeezed. And so what you find is that the effect of lensing on the CMB is similar to that of galaxies, a combination of magnification and shear. And the reason why this matters is the following. So if the lensing of the CMB has those two spatial symmetries, so a monopole for magnification and a quadrupole for shear, the extragalactic foregrounds, on the other hand, have different symmetries. They're typically made of spherical halos or point-like galaxies. And so their effect on the local power spectrum is only a monopole. And so naively, you would expect foregrounds to only bias the magnification, but not the shear. And so if you can split your standard CMB lensing quadratic estimator into a shear-only and magnification-only estimator, you might be able to remove the foregrounds. So to test these ideas, we look at realistic simulations of these foregrounds from Nilima Segal and collaborators. And so you've seen this plot again, you've seen this plot already of the standard bias. And if instead you look at the magnification-only CMB lensing estimator, what you find is an even larger bias, as you would expect, because foregrounds look most like magnification. And if, on the other hand, you look at only the shear part of the CMB lensing, what you find is that the biases are really significantly nulled. And so this is a case of relying on the symmetries of the problem to get rid of a systematic effect. And it is a powerful one because it appears to work on all extragalactic foregrounds. And it's very effective at nulling the bias. And as a result, because of this, it allows you to extract information from smaller scales in your CMB maps. And so you can actually gain signal to noise. So not only do you reduce systematics, you also increase your statistics. This was an example of using spatial symmetries, monopole and quadrupole, to remove foregrounds. We can actually go quite a bit further with methods like bias hardening that I won't tell you too much about, and combining these methods with multi-frequency analysis. And so I just wanted to highlight the work of Noah Saylor and Omar Darwish, grad students who have made a lot of cool progress on this question. I also wanted to point out that the CMB secondary anisotropies like thermo-SZ and KSZ are another bias to lensing because they too come from cosmological distances and they too are lensed. And so Nishant Mishra, as a first-year undergrad, produced his first paper and the first calculation of this effect. And so I just wanted to highlight this work. And finally, some of these methods to get rid of foregrounds that we've developed for CMB lensing also apply for intensity mapping, so a completely different field. And a lot of it has been the work of Abhishek Maniar. And finally, the question of foregrounds also applies in polarization and not just temperature. We have work in progress with Maris Milia on this question, and so more coming soon. So this is all I wanted to tell you about some recent progress on CMB lensing measurements. So those shadows of the mass and how leveraging the analogy between CMB and galaxy lensing allows you to improve CMB lensing measurements. So again, now is probably a good time if you have some questions to gather your thoughts and either post them on Slack or keep them for the live discussion. Okay, moving on to the second part of this talk and switching from CMB secondary anisotropies that have to do with gravitational potential to CMB secondary anisotropies that have to do with Thomson scattering. I would like to tell you about those shadows of the gas and the fact that around every single little galaxy in the universe that you might be seeing in an optical survey, you may not suspect it, but there's actually a giant gas cloud that would be pretty much invisible if it weren't for the backlight of the CMB. So why would you care about the gas around the galaxies? Aren't we supposed to care about dark matter and dark energy? This is the ordinary stuff that we know. And I would argue that there are two reasons why you should care about the gas. And to illustrate this, if you look at this cosmological simulation from Illustris, what you see here in blue is the dark matter distribution. And what you'll see soon in green and red is the distribution of the gas, the ordinary matter. And while the gas at first mostly follows the dark matter, what you can surely see in the simulation is all the fireworks that are going on. These are supernova explosions and energy output from accretion onto supermassive black holes. And these effects are effectively feedback in galaxy formation. They're a form of feedback. They regulate galaxy formation because they push the gas far outside of the dark matter halo. And there, the gas is typically too diffuse and too cold, and therefore too faint to detect in emission. And this has been called the missing baryon problem. And so if you could localize those baryons, if you could localize this invisible gas, it would tell you about the amplitude of those feedback processes, which are currently the biggest uncertainty in galaxy formation. So revealing this gas with shadow on the CMB is a key way to learn about galaxy formation. And in fact, even if you don't, if you're not interested in galaxy formation, you're only interested in fundamental physics from cosmology, I would argue that you still need to know where this gas is because ordinary matter is about 15% of all the mass in the universe. And so you cannot analyze percent precision logical structure data if you do not know where 15% of the matter is. This problem for logical structure is not just for future data. There already are tensions in the logical structure on small scale. The tension I'm showing here is the so-called lensing is low on small scales. And what is being plotted is the mass density profile around galaxies, measured by galaxy lensing, as a function of distance from the center of the galaxy. Please don't be alarmed by the weird S shape of the plot. This has to do with how things were plotted. But the main point to take away from this plot is that the theory expectation in red, if you assume that the baryons follow the dark matter, overestimates the signal compared to the actual measurements, which are the green data points. And so there are many potential reasons for why that would be. But the question I would like to ask is how much of this tension is due to baryons? And if you push the baryons away from the halos, at most what you can do is completely get rid of all the baryons. If you do this, what you get is the red dashed line. And so while this may not completely solve the tension, you can see that it could be a big part of it. And so what we'd like to know is, where is the truth between the solid red curve and the dashed red curve, and use the CMB as a backlight to answer this question. So I mentioned a few times these Sunyaev-Zel'dovich effects, so it's probably high time I explain what they actually are. These are the change in the energy of CMB photons, this red photon you see here, as they bounce off moving free electrons in the hot plasma or the hot gas around galaxies. And as they bounce off moving free electrons, they experience a Doppler shift. This is really like playing tennis with CMB photons, where the CMB photon is a tennis ball and the free electron is a tennis racket. So depending how the racket is moving, the CMB photon or tennis ball will acquire or lose energy. So there are two types of Sunyaev-Zel'dovich effects because there are two types of electron motions. The electrons are first moving because they are hot, and so this thermal motion gives rise to the thermal SZ effect, or this TSZ effect, and it tells you about thermal motion and therefore the temperature of the gas. It also tells you about the gas density because, simply put, if you had no gas, you would have no effect. The second source of motion is due to the bulk motion of the gas, so the whole gas cloud moving towards or away from you. And this effect is therefore called the kinematic Sunyaev-Zel'dovich effect. Again, it's a Doppler effect, and so it tells you about that bulk velocity. And again, it tells you about the gas density because, again, if you didn't have gas, you would have no effect. And so if you can measure those two types of gas shadows, those thermal and kinematic Sunyaev-Zel'dovich effects, you get to measure the gas density and the gas temperature. And so this really tells you about the thermodynamics of that gas. These probes are also unique in many ways in terms of the mass and redshift range and the distances from the center of halos that they're able to probe. So if you'd like to learn more about this, please again, don't hesitate to post your question in Slack or ask it during the live Q&A. But let me show you what the effect looks like for a typical massive galaxy. So what you see here on the right is an optical Hubble image of a boss luminous red galaxy. And this whole image fits within the central pixel of the CMB map that you see in orange and yellow. And so we clearly do not expect to resolve the galaxy itself. In fact, our resolution is the inner white dashed circle that you may be able to see. However, the extent of the halo around the galaxy is much larger and given to you by this outer white circle. And so while our resolution does not allow to resolve the galaxy, it's plenty sufficient to resolve the halo. And it may tell us about where the gas is. But if you look at this image, this cosmic microwave background image of the galaxy, what you see is simply noise. The signal is much too low for you to detect anything on a single galaxy. And so what we did there is use the fact that the BOSS catalog had hundreds of thousands of galaxies, and we performed stacking analysis. And so as you run the stack, as you add more and more galaxies, the noise gets beaten down, and the shadow of the gas, this thermal Sunyaev-Zel'dovich effect, starts to appear. And what you can see is that this dark shadow, which tells you about the gas around the galaxy, is way more extended than the galaxy itself, which again fits in the central pixel of this image. And the resolution of an experiment like ACT is now sufficient to probe that gas profile. So this was the thermal Sunyaev-Zel'dovich effect, which we measured with stacking analysis. For the kinematic SZ, the situation is a bit more complicated because of this bulk velocity dependence. And so as an object is moving towards or away from you, this changes sign. And so if you simply stack CMB maps at the position of the galaxies, the signal will cancel out and average down. And so to detect the KSZ, you need some way to avoid this cancellation. And the methods we pursued has to do with getting an external handle on the bulk velocity from the positions of galaxies. So this is called velocity reconstruction from the density field. Really, it's simply Zel'dovich approximation or linear theory, which relates the velocity of matter to the density field of matter. And simply put, what this equation says is that if you have more matter here, it's because the matter has been moving towards there. And while this may seem extremely simplistic, it turns out to work extremely well on simulations. And what you see in this image is the whole bus LRG or CMAS and LOSI catalog. So you are here in the center of this 3D box. Each point is a galaxy, and color-coded in blue or red is our estimate of their line-of-sight velocity from this process. And so for every single galaxy in the sample, we have an idea of whether they're moving towards or away from us. And we can now weight by this velocity information in the stacking analysis. And when we do, this is what we get here on the left. This perhaps uninspiring yellow blob at the center is actually one of the highest significance KSZ measurements to date, 6 to 8 sigma. And the fact that you're able to see it by eye shows the significance. And so with those measurements of kinematic and thermal SZ for the same galaxies, what we have is access to the gas density profile and the gas density times temperature or pressure profile. So we're able to resolve the gas well, we're able to probe its thermodynamics, and show that the gas extends way beyond the extent of the dark matter profile, so this virial radius. And this is a key input for feedback modeling. But going from galaxy formation to cosmology and this question of how do we model percent precision large-scale structure data when we don't know where 15% of the mass is, this is a place where kinematic SZ can help a lot. So again, in galaxy lensing, you typically look at the shear of, or the ellipticity of background galaxies around foreground galaxies, and this tells you about the total mass, dark matter plus gas mass around your galaxies. But if you don't know where the gas is, you have a big uncertainty in your modeling. And if you do the same stacking analysis with KSZ, what you get is only the gas profile. And so there's almost no modeling involved. You can basically subtract these two measurements and get rid of the gas in lensing and end up with a clean lensing with dark matter only. And so you've seen this plot already of the tension between a small-scale measured lensing and expectation if the baryons were to follow the dark matter. We can now add the curve to this plot from our KSZ measurements. And this is what you see. And so again, as expected, it does not solve the full tension, but it is a significant part of that tension and something you definitely want to get right in order to move forward. And so the current precision of KSZ measurements, even 6 to 8 sigma, is already sufficient to answer this question for current lensing measurements. And in the future with Simon's Observatory and CMB-S4 will be sufficient for solving that baryonic uncertainty for lensing from LSST. So again, a lot more going on this front, and I just wanted to highlight the work of Stefania Amodeo on interpreting these curves in terms of thermodynamic profiles around galaxies and this lensing curve that I just showed you. Also the work of Emily Moser on using TSZ and KSZ to constrain galaxy formation, and some of the challenges you face when comparing to simulations. And then work with a number of collaborators on doing consistent joint analysis between SZ, lensing, and potentially redshift space distortions to get rid of that baryonic uncertainty and extract more cosmology from the large-scale structure. And finally, while the lensing I talked about was really galaxy-galaxy lensing, we are working on doing this for cosmic shear, the autocorrelation of galaxy lensing. And there are a few more challenges, but also there's a few reasons to be hopeful, and so please feel free to ask about this if you're interested. So this is all I wanted to tell you about scattering anisotropies, those gas shadows, how they allow us to localize the missing baryons, which is important not only for galaxy formation feedback, but also for cosmology by solving the baryonic uncertainty in lensing. And finally, while I didn't present it, because the kinematic SZ tells us about velocities, it is also an excellent probe of the ultra-large-scale structure in ways that are hard to do with galaxy clustering alone. So this is all I wanted to say about these CMB secondary anisotropies. And in the last couple of minutes, I just wanted to say a few words about the very near-term future of these measurements. And the key thing I wanted to highlight is this Dark Energy Spectroscopic Instrument, which has already almost completed its first year of data. And so these are images that I took of the Mail telescope where Daisy is sitting in Arizona back in 2020 when the experiment was being commissioned. Since then, Daisy has collected more spectra than any other spectroscopic survey to date. It's basically an order of magnitude increase in the sample size, which directly translates into statistical error bar. And so I'm really excited for all of the Daisy cross CMB analyses. And I'm one of the contact people for all the Daisy cross ACT joint projects. And so you should expect to see a lot of cool stuff coming out of this. And so finally, to summarize, the CMB secondary anisotropies are useful for answering a number of key fundamental physics questions. These have to do with neutrino masses, dark energy, inflation, dark matter, but also the astrophysics of galaxy formation. We are about to obtain data from unprecedented large-scale structure and CMB experiments, which are really going to transform this field. And these really turn the cosmic microwave background into a large-scale structure probe, a unique one in terms of redshift range and in terms of the properties of the large-scale structure that it reveals through its shadows. Again, much like you would reveal a watermark on a banknote. And so I just want to leave you with this picture at the bottom that shows how when you look at a galaxy in optical like you typically do, while this galaxy may be too small to resolve in the CMB and fit in the central pixel of the CMB gives you a picture of the total mass, the gas density, the gas pressure, the dust emission, and so many properties of those galaxies that would be hard to observe in any other way. So please stay tuned for a lot more. And please join the live Q&A session. Thank you so much.